Hello guys, so in this video what I want to do, I want to derive and talk about the idea of variation of parameters for solving differential equation in a case if you want to find a particular solution. So yeah, let's talk about that. So first, since we're going to talk about differential equation, then let's consider this linear non-homogeneous differential equation, which is going to be of the form constant a times y double prime plus b times y prime plus c times y is equal to some function f of t. So what is the idea of the variation of parameters? If you want to find the solution for differential equation, then you know that as a first step, you need to find the solution for homogeneous part. And what is the homogeneous part of this differential equation? It's going to be just the original differential equation, which I'm going to call star, where right-hand side, or in other words, our function is going to be 0. Yeah, and if we have this differential equation, there's like a certain procedure what you need to follow to find a general solution. Yeah, but variation of parameter is going to be about finding the particular solution. So, for example, let me just do one simple example that I'm going to show you. Consider the differential equation of the form y double prime minus 3y prime minus 4 is equal to t. So according to our approach, let's first find the solution for the homogeneous part. So I want to find the solution for differential equation of the form y double prime minus 3y prime minus 4 is equal to 0. And then to solve this differential equation, what do we need to do? We need to replace every y prime. So we're going to replace y with 1, y prime with r, and y double prime with r squared. So in other words, we're going to generate this quadratic equation, which is r squared minus 3r prime minus 4 is equal to 0. And then by factoring this quadratic equation, you're going to obtain r plus 1 times r minus 4 is going to be equal to 0. So we're going to obtain two roots, r is equal to -1 and r is equal to 4. And as soon as we know our r, we can write our general solution as y general is going to be equal to some constant c1 e to the power of -t plus some constant c2 times e to the power of 4t. And that is going to be our general solution. And actually, let's indicate this example by star. And then what is our second step? Our second step is going to finding a particular solution. So in other words, we want to find some function y particular, such that if I'm going to that y particular and plug in inside my differential equation, and if I'm going to compute the second derivative of y particular multiplied by constant plus the first derivative of y particular multiplied by constant plus our function itself, then what I'm going to obtain in the end I'm going to obtain function f of t. So you can see for our general solution, if I'm going to plug in this solution, this y general, inside my differential equation, then what I'm going to do, I'm going to obtain 0 in the end. But for y particular, I'm going to obtain f of t in the end. So the variation of parameters, I can show you the first approach how to find the y particular, but the idea of the variation of parameters is going to be a second approach, how finding y particular. But before that, let's do and find the first approach. So here you can see that my function is going to be t. And we know that we're going to take our first derivative, our second derivative, and yeah, here I forgot type, this should be just minus 4y. Then what we're going to do, we're going to guess our function. And I'm going to guess my function as to be, let's take y particular is going to be equal to at plus b. And then we're going to, what we're going to do, we need to take our function, plug in inside our differential equation, and figure out what is going to be a and what is going to be b. So right now a and b is unknown. But as soon as we're going to plug in the differential equation, we can solve for them and figure out what they are. So for that, let's find y prime. So y prime particular is going to be equal to a. And you can see y double prime particular is going to be equal to 0. So what I'm going to obtain? I'm going to obtain 0 plus minus 3 times y prime particular minus 4 y particular is going to be equal to t. So if I'm going to plug that in, I'm going to obtain minus 3 times a minus 4 times at plus b is equal to t. And then what I'm going to obtain? I'm going to obtain minus 4at plus minus 4b minus 3a is equal to t. And you can see that the right hand side you can write as 1 times t plus 0. So then from here I'm going to know that minus 4a is equal to 1 and 4b is equal to negative 3a. And if you're going to solve the system, you can see that we're going to obtain that a is equal to negative 1 over 4, and then b is going to be equal to 3 over 16. And if I'm going to replace my a and b as a constants with those values, then that is going to be exactly the solution as y particular. So in other words, if you're going to take this y of b and plug in inside your differential equation, after you're going to differentiate and compute your differential equation, the expression in your differential equation, you're going to get t in the end. So variation of parameter is going to be about what if on the right hand side I'm going to have some function which is not obvious as t. I'm going to have some f of t. Is there going to be another approach finding y particular when your right hand side is going to be too complicated and you cannot just guess a function and do what we did for this problem? So what we're going to do right now, we're going to derive the approach that we can use to figure out y particular. So for that, assume that we have our differential equation, and for this differential equation we can use what we did before, taking the homogeneous part and finding the solution, but assume that we have two linear independent solution, y1 and y2 of the homogeneous part for our differential equation. And then what we're going to do, we're going to find y general as taking like some constant c1 times y1 plus c2 times y2. And remember here, like y1 and y2 are functions. So variation of parameters is going to go the following way. We're going to take our constants and make them a function in terms of t. So in other words, I'm going to define my y particular in terms of t as c1 as a function in terms of t, y1 as a function in terms of t, plus c2 in terms of t, and y2 in terms of t. So the goal is c1 and c2 right now is going to be some parameters, and they're depending on t, so that's why it's called variation of parameters. And there are some unknown functions. And the question is, can we figure out what is my c1 and c2 such that they're going to satisfy this differential equation from one side, and from the other side, that the functions we're going to get y of p is not going to be either your y1 or y2. Okay, so for that, what do we need to do? We need to kind of solve for this for that function y of p. What do we mean by solve? We have our differential equation, we have some possible solution which is unknown, but that we want to figure out. So what I'm going to do, let's take our solution and just plug it inside differential equation and see what we're going to obtain. So for that, I'm going to just drop my t. So I'm going to have that y particular is going to be equal to c1 y1 plus c2 y2. So let's just find the derivatives, and the first derivative and the second derivative of y particular. So the first derivative is going to be y particular prime is equal to c1 prime y1 plus c1 times y1 prime. For the second one is going to be c2 prime y2 plus c2 y2 prime. Okay, and what about the second one? For the second derivative, I'm going to obtain c1 double prime y1 plus c1 prime y1 prime, and that's going to be using the product rule for the first term over here. And you can see I can do the same for the other three terms, and I'm going to get this expression over here. Then what we can do technically, we can take those derivatives and our function, plug in inside our differential equation, but that is going to be really messy. So instead, what I'm going to discuss, I'm going to use the fact that if I'm going to take my, let's say, y1 or y2, and plug in inside my differential equation, then I'm going to obtain ay1 double prime plus by1 prime plus cy1. Then since their solution for the homogeneous part, then I'm going to get that their sum is going to be equal to 0. And we're going to use this fact because then take a look at this term over here. I'm going to actually use circles, c1 y1. Then we're going to take c1 y1 prime and c1 y1 double prime. And you can see if you're going to plug in them inside the equation, then you're going to have coefficient a for double prime, b for prime, and c for your function, and c1 for each of the term is going to be the common factor. So you're going to obtain c1 times actual a y1 double prime plus b y1 prime plus c y1, which is exactly going to be equal to 0. So in other words, we can ignore these terms. If you're going to do the same for y2, then you can see that I can ignore c2 y2, then I also can ignore c2 y2 prime and c2 y2 double prime. And right now we have -6 terms. So what else? We have these two terms for y prime, and remember that we have c1 and c2, that's two unknowns. So in order to figure out those two unknowns, we need to have at least two equations. And this is going to be exactly our first restriction, or in other words, our first equation, because I have no idea how c1 prime y1 and c2 prime y2 are related to each other. But what I can say that I want to find function c1 and c2 such that c1 prime y1 plus c2 prime y2 is going to be equal to 0. And that is exactly going to be my first restriction, or in other words, my first equation. But then observe, if this expression here is equal to 0, then when I'm going to take the derivative of this expression, the derivative is also going to be equal to 0. But derivative of that expression is going to be this term over here, so I can neglect that term, and is going to be my third term, so this term over here, which also can be removed. And again, that works because if equation itself is equal to 0, then the derivative is also equal to 0. Okay, so let me erase the derivative. And then we're going to obtain our second equation. And our second equation is going to be the following. You can see that if I'm going to plug in to my differential equation those three functions, yp, yp prime, and y double prime p, then what I'm going to get in the end I'm going to obtain just these two terms, which is going to be c1 prime y1 prime. So let me write them down. And since we have constant a, then I'm going to have so let's actually write me down in this black cloud. I'm going to obtain, after plugging in all those functions at my differential equation, a times c1 prime y1 prime plus c2 prime y2 prime is equal to f of t. And if I'm going to divide both sides by a, I'm going to get exactly the second equation for finding unknown functions c1 and c2. So I'm going to have c1 prime y1 prime plus c2 prime y2 prime is equal to f of t. Okay, and you can see that right now we have two unknown functions and we have two equations, and using some linear algebra, which I'm going to show in a second, we can figure out what is going to be my c1 and c2. So first observe that we have the common term, almost common term here is c2 prime y2 and c2 prime y2 prime. So what I'm going to do, I'm going to multiply the first equation by y2 prime, and the first equation, as the second equation, I'm going to multiply by y2. So what I'm going to obtain, I'm going to obtain the following. I will have c1 prime y1 plus c2 prime y2 prime y2 is equal to 0. And then for the first one, I will have a c1 prime y1 prime y2 plus c2 prime y2 prime y2 is equal to f of t times y2. And then I'm going to take these two equations and I'm going to subtract the first equation from the second one. And what I'm going to obtain, I'm going to obtain C1 prime Y1 prime Y2 minus C1, oh, sorry, here I forgot to multiply by Y2 prime. So let me fix that. So it's going to be C1 Y1 times Y2 prime plus 0, because this term and this term are identically the same, so they're going to cancel out, and equal to f of t times y2. And then if I'm going to factor c1 prime, I'm going to obtain that c1 prime is times y1 prime y2 minus y1 y2 prime is equal to f of t times y2. And finally, if I'm going to divide both sides by this expression over here, I'm going to obtain that c1 prime is equal to f of t y2 over y1 prime y2 minus y1 y2 prime. Okay, and we're going to get this kind of differential equation. But actually, on the right hand side, you can see, I forget something. Yeah, here I did a mistake. It should be f of t over a. Sorry about that. So that's why I'm going to have this f of t over a, and this is f of t over a. So here I'm going to multiply this by constant a. Okay. So we're going to get on the right hand side that I know what is my f of t. I know what is my y1, y2, and their derivatives, and I also know what is my function a. So actually what I can do, I can integrate both sides. And if I'm going to integrate both sides, I'm going to get that c1 is going to be equal to the integral of that function. So c1 is not going to be an unknown function anymore. c1 is going to be the integral of this function. Using the same approach by multiplying these two equations by another function, which is going to be like y1 prime and y1, I'm going to get that c2 is going to be equal to, funny story, I recorded the video and it wasn't recording, so I'm going to just repeat what I just said. So then our c2, if we're going to do the same approach, is going to be equal to the integral of the dead function. You just need to do the same. You need to multiply your equations by y1 and y1 by y1 prime and y1 and just do subtraction, and you can check this as your homework. And after that, we figure out what is our c1 and c2. So what we can do, we can just take them as a functions after we're going to integrate them, plug in our y particular from the equation that we started, and if we're going to multiply them by original solutions y1 and y2, we're going to find our y particular. You can see that this second approach is slightly longer, but it works for sure if we can figure out and compute those integrals in a closed form. And I'm probably going to make one video for which I'm going to find y particular for our previous example, and that's it. Okay, yeah, so this was my first differential equation video. Let me know if you have any questions. If you're not subscribed to my channel, please subscribe, and have a nice day.